today. Missing. He's currently sat on tarmac, I believe, in Manchester, trying to fly across to Europe. But that talk, and if I seem to have a really bad connection, hopefully you can hear me. The video is going to cut out. I'm going to bring Uma onto the online. So,
Hey Paul, I'm missing out a couple of. I think I'm not able to hear you completely. There's a little dropouts in the middle.
that's the connection issue that we talked about.
Okay.
So yeah, I'm back now. So yeah, so this is the connection issue. I'm going to pass to you because you've got a good solid connection to introduce yourself.
Okay, great. I guess that's a cue for me to go. So, thanks very much, Paul and John, for this opportunity. I hope you can all hear me okay. If you can't, please just put some comments in chat, and I can just follow up on your request. So, thank you for this opportunity. So, I'm a professor in computer science at Cardiff University. Excellent. Thank you, William. So, and I work with part of the National Edge AI Hub with Rajiv Ranjan from Newcastle University. So this talk is really about how we try to identify the importance of edge computing. What does that mean, and how does AI connect with edge computing? You can there's my email there, my Twitter link. So just you follow if you're interested in discussing some of these ideas. Please come back. Okay, so let's just start off the talk. So to start off the talk, I just wanted to give some context. There's something we call the edge cloud continuum. So essentially, we have at the bottom of this image, you can see a number of devices that we have available in proximity to a user. So we have wearable devices, we have vehicular systems, for example, we have robotics, which are becoming more and more important, humanoid robotics and industrial robots. Then we have home automation and connected buildings, so we can have energy in proximity to our buildings, photovoltaic panels, and other types of energy sources. And of course, we have medical imaging and other diagnostics that can also sit at the edge. So all of these are devices that often channel their data through a backbone network. And the network itself is changing over time. So we have things like optical networks currently with ability to have intelligence directly in the network, something often referred to as cognitive networks. And ORAN, which is this concept of a radio access network, an open radio access network that can be controlled and managed by different operators. And this data is then channeled into a cloud data center, right? So you can have a single data center from a single provider, such as Microsoft Azure or Amazon Web Services, but you can also have federated data centers, right? These data centers can sit in different geographical locations. And these data centers often run virtual machines to they run virtual machines to container frameworks to increasingly something we call functions. So these are things like Google functions, Amazon Lambda. I'll come to these in a minute. But so the idea is that we connect our edge devices through a backbone network into a cloud data center. However, things are changing, right? The network is becoming programmable, is becoming more open to things like software-defined environments, but also the ability of the edge is becoming more and more intelligent. So edge devices can have different data rates from megabits per second to terabits per second, different power consumption profiles, and different processing profiles. So we can do things like, mobile edge, we can have edge caching and data storage, we can have edge analytics. Also, we can embed edge computing directly within devices. So what that means really is that the edge, the cloud is no longer the data center, right? The cloud is all of this, right? So the cloud is a data center plus the network plus edge devices. So what this provides us is the capability to have services, new types of digital services, which cut across these three layers, right? So we can have user-owned devices or we can have process automation controllers that sit within factories and other environments. And so we have a new playground right now, a new computational infrastructure, a systems infrastructure that enables us to do AI. And that is what we call, from my perspective, Edge AI. Edge AI is the ability to integrate these three layers and connect these three layers to build the next generation of services. And in the future, right, we will also have quantum clouds where we have access to cloud computing to run specialist cloud hardware, which follows quantum computing ideas. And also we have quantum accelerators, which will be room temperature quantum, right, which sit at the edge. So we're connecting quantum devices along the same type of model. And the rest of this talk looks at this playground, the systems context for the use of AI services. And so we can have federated edge learning, and we can have functions which, again, stretch across this layer from edge devices in network functions, which can do partial processing of the data while the data is in transit, from migrating from the edge device directly to the data center, right? So this is where we are really focused on here. And so this thing that you see in that red box is where the rest of this talk will be focused on. And just to give you a context. To give you the kind of current state of the art in this way, so we work with Fermilab. Fermilab is a particle accelerator like CERN. And so what Fermilab talks about is that if you look at our current Internet of Things and mobile devices, and we look at these two axes, right? We have the data rates in terms of bytes per second on one axis, and we have computational time in terms of the time it takes to process something. Our mobile and Internet of Things devices sit around this range. So you have 10 to the 6 bytes per second to about per second execution or 0.1 second execution on these devices. If you look at state of the art of where our mobile devices are, this is where these high-end physics labs are operating. So if I look at a qubit readout, this is from a sensor that is built using quantum materials to what we call an event trigger action, which sits in a particle accelerator, right? This is where we are in electron microscopy, plasma control algorithms within, or in LHC center, the Large Hadron Collider sensor. So looking at 10 to the 14 bytes per second with a 10 to the minus 7, right, time for processing. So the question is, right, how do we move from here to somewhere up there, right? Because if you look at the way technology has progressed, stuff that used to happen in our high performance computing infrastructure is slowly moving towards our laptops, towards our desktop. So if you look at the same concept for Internet of Things, right, the question is, how do we move our Internet of Things, which you and I use on a daily basis, from here to there? And the way you do it is to have hardware acceleration of machine learning models. So what Fermilab is doing is they're creating this hardware acceleration architecture called HLS for ML. You can download this one. There's a GitHub repository for this. So what happens is you encode your neural network model using something called ONNX, which is the Open Neural Network Exchange. You then translate it using a quantization model, which is hardware specific. So we have different variants on this. QKeras from Google or Brevitas from AMD. There's Hawk, for example. So what you do is I think I've lost my slides for a minute. Let me just see if I can. Great, perfect. So then you can use HLS for ML, and then you can map this specialist neural network model into hardware like FPGAs or application-specific integrated circuits, right? So this is really where we are looking at the future edge, right? Because the edge will have hardware-accelerated architecture that can host these machine learning models. Okay, so continuing on from this, we've tried this at Cardiff. We took HLS for ML. And the idea is we took a machine learning model, a convolution neural network in this case, and we put it into a hardware description language called VHDL. So the idea is your neural network itself is encoded in hardware using VHDL. And what you can do is you can have a user who moves around the city, and the user carries with them a hardware description version of a neural network. So what happens is that when you start with one data center, which is over here, and you move to a different data center, you take your machine learning model, encode it in a hardware description language, and you push it to an FPGA architecture. So essentially, you're carrying your hardware description or hardware configuration in an VHDL file, and you push the VHDL file to a data center, an edge data center that hosts these FPGA hardware. So we've tried with things like Tiny Llama, which is a large language model for tiny devices, and you can run these LLMs at the edge, but these LLMs are then encoded using this kind of hardware description. And this is an example. We've run this on a Vertex FPGA board. This is a Xilinx Vertex board. And so we used a data set with about 500 vehicles within the city of Luxembourg with a 10 kilometer by 10 kilometer size of the city, about 144 edge nodes at 74 megabits per second. And we can see that if we compare this convolution neural network implemented in hardware using VHDL running Keras, we can get a performance improvement of 200% to 5,000% compared to a Intel Core i7 machine. So it's a processing speed of about 65 nanoseconds with an accuracy. So we decrease in accuracy from about to, we have a loss in accuracy, but we have an improvement in performance in terms of processing performance. And the hardware description language itself is encoded in about a 1.1 megabyte file, right? So this is where we feel the future of the edge is. The future is specialist hardware coprocessors that can be tuned to run machine learning models, which sit at the edge, but then communicating with backend cloud infrastructure in the kind of continuum model that I showed you. Okay, so based on this concept, I will introduce 3 research challenges, right, that I think are really relevant for this area. So the first question is, how do we partition our machine learning algorithms across this continuum? What should run on the edge? What should be in the network? And what should run on the cloud? This is often referred to as a computing continuum. So our machine learning is no longer, very large language models just sitting in the cloud, but they're also distributed to other resources along the continuum. And how do we do this in taking account of data privacy, capacity of the resource, the resilience, availability profile of the resource, and energy consumption of the resource, right? So that's the first question. With increasing availability of accelerators like GPUs and other hardware-specific AI accelerators, and in the future, quantum accelerators that are room temperature. In fact, there's a German company called Quantum Brilliance, which is actually shipping quantum accelerators you can run at the edge, but at very low qubits right now. So the other question is, can machine learning algorithms be adapted to the characteristics of devices on which they're hosted, right? So if I take a machine learning model and I run it in a data center versus I running it on a machine closer to the user, does the algorithm need to change? Right? So how does it change? What does this mean for the stability or convergence of the machine learning model versus its performance? So for example, if I take a hardware device and I power cap it, so I say, I want you to run the best machine learning algorithm you can, but this power consumption profile, how does the model change? How does the algorithm change? Right? So that's the research question, right, that we are currently considering here. And the final question is, right, that if you looked at the cloud continuum where you have the edge device, the network, and the data center, right? Because a model is now split across 3 resources, how do you know what's going on, right? Because explainability becomes an even bigger challenge now because your model is no longer in one place. Your model is fragmented across the continuum. So how can we use approximations, right, as a way to explain what's going on? Because we have a workflow, a collection of functions running in different places. And so these are the 3 research questions, right, that the rest of this talk will build upon along the cloud continuum picture that I showed right in the beginning. And please post your questions in chat because I'm looking at that while I'm talking, so I can focus on specific elements of this talk. Thank you. Okay, so let's look at one example application, right? Because all of that was a little bit conceptual. So this is an example of an application that really requires the edge. It's an example of a rural application, like, for example, in farming, where I have a number of farm robots. I can have drones that spray crops. I can have farm picking robots. Or so what I do here is that because the farm is in a rural community, a rural area, the backend network is very limited because there may be no 5G network in a rural environment. So that means that these robots have to operate and collect data, and therefore the farm needs a local cloud server. We call these field side servers. These servers are coordinating the operations of these robots, but they're also collecting data from these robots. Because the backend connectivity to the data center or to the cloud is limited, I need to push as much processing I can closer to where the robots are on the farm. Right? So that's a typical example of an edge. Where the edge needs to add value, the backend connectivity is limited. The backend has very limited connectivity. And also, these farms might talk to nearby farms. There might be a connection between a server on this farm and a server on the nearby farm. You might have renewable energy generation in proximity to the farm, which we call edge energy. So we have edge energy driving an edge server, but the backend connectivity is very limited. So we need orchestration mechanisms, right, that prioritize processing on the edge. And you can see those two papers that explain this in a little bit more detail. And I'll go through one application of this. So this is an example. So we have this project called Rural AI. The Rural AI looks at these data processing pipelines that can build on this edge model. So I have something like a sensor that is soil quality sensor. I can have a surveillance drone, right, that sits in a field. The surveillance drone has a camera, and the camera can take images from the crop, and it can store these images directly in an SD card that is contained on the drone. And I can also have special cameras, right, that are pointed at the crop and can monitor this data from the video feed. So I have a Kafka stream, which is a real-time stream of events coming from the sensors. I can have an FTP storage that stores the SD card data, and I can have a video processor that looks at data coming from the video stream. I apply all of this processing now, but on the farm itself, right? So this is on-premises computation done on the farm. So I can have an edge convolution neural network, I can have drone image mapping, and I can have quality assessments. And I can run a collection of services, right, that run on the farm. And then these services connect to a backend data center, right, that can then do aggregation or additional processing beyond what I'm able to do on my edge device, right? So that's the idea. So if this connectivity breaks to the edge data center, I'm still able to do partial processing, but on premise where the data center on farm is located. So data combined with other robots or field side units. Robots and field side units can be realized as single board computers, and you have intermittent connectivity between the robot and these field side units. So just have a look at that website that explains this model in a little bit more detail. So you can think of this. So I have a robot that does weed detection or weed removal. So I can have images coming from the robot. They have different types of image quality. So I can have the direct image. I can have a blurred image. I can have an image which is kind of blocked out. I can have a blank image. So we used a real data set of weeds in order to see what happens when you have a robot that sits on premise on the farm. It has a camera on the robot, and processing is done directly on the robot, right? And then the robot offloads the processing to a field side unit that sits on the farm, and the field side unit then communicates periodically using a low intermittent network to a cloud data center. This is a typical example of where the edge adds value to what a cloud computing is able to provide, right? So limited network infrastructure and distance from compute resources represents network latency, affecting data communication quality in the robot and the field side unit. So that's just one example of agriculture and field side units. And just continuing on from this, so this is the model, right? I have a server that sits on the farm. I can have multiple robots or data sources that sit on the farm. So here we use a particular implementation called FuncX. FuncX is a Python library that can run functions directly on distributed data centers. And the idea is that this connection from the data center to these clusters, it can be intermittent. So this paper explain this in a little bit more detail. So that means this failure rate, alpha, beta, and gamma, is a failure rate that models the connectivity of this network. And we can change this failure rate to see what happens in the type of data we collect from these farms, right? So you can kill this network, so you lose some kind of connectivity. So what we were doing here in this example application is we're doing federated learning, right? But under uncertain network connectivity. So that's the idea. So sometimes this federated node is available, sometimes it's not, right? So that's the idea. And so we can here explain the idea that ideally, if everything is done on a cloud data center, we'll have an accuracy of say 100%, right? If you do it only on one site, so if it does only on location A, location B, or location C, this is the kind of accuracies we get on the VEEDS data set that I just showed you, right? So if you do it on only one site, we have about 30% accuracy or 50% accuracy. Here, what happens is we start federating multiple sites. So our accuracy improves, right? But under intermittent connectivity. So what this shows me, this value of n equals 25 to 100%, shows me that to what percentage are the other federated sites available for me to connect to them in order to build this aggregate model using federated learning. Right, so is one site available? So can I get 25% of the sites? Can I get 50% of the sites? Can I get all the sites together? And you can see that our performance changes. So with all the sites, we are reaching about a 90% accuracy. It's still not as good as a single cloud environment. If we're able to push everything to a cloud, we still have the best accuracy. But here, right, we are able to utilize our edge resources more effectively. Right, so that's just one example of an application, a real application. And then this shows you the participation rates. Red is site A, blue is site B. So we can use different sites depending on their availability profile. Right, so you can see that site A has a lower availability profile compared to the other sites. And here, when all the sites become available, we have the highest accuracy. In this case, reaching about 0.86%. Sorry, 86%. One being the maximum that we can get. Okay, so that's just one example of this kind of architecture. We have another project that looked at this farm concept a little bit more. This was a DCMS funded project with Cisco. It has a number of companies involved: Utterbury, Appway, Jam Digital. We had other two local authorities, Glenogwent, very close to Cardiff, and Monmouthshire. Both of these are classified as rural communities. And so what we had is we had a farm with a camera feed coming from the farm. And this was the kind of architecture. So we have a Cisco Meraki camera. The kind of benefit of Cisco Meraki is that these cameras from Cisco have a built-in edge device, which can pre-process the data before it's shipped out. So we can take a RTSP real-time data stream, which comes from the farm. We process it with YOLO, and we have a broker that looks for particular events in this data stream. And if that event is triggered, that particular object is detected, that broker triggers an alert to a smartphone of the farmer. And the key thing we were looking at is farm theft. People are stealing things from farms, or events are happening on the farm. So what you do is you can detect particular objects on a farm. And either you can go through this route, the top route, where you take the raw data stream and process it, or you can take a pre-processed data stream that is directly being processed at the edge. So the camera uses an inbuilt edge device to process the data stream. And then we have a pub-sub model, an MQTT broker with a publish-subscribe model, which subscribes to particular events from the stream. So we don't need to do YOLO anymore, because the YOLO equivalent is directly done from the camera. Right, so we then have a smartphone that connects to an MQTT broker and a Raspberry Pi subscriber that subscribes to particular events of interest. So both of these are examples of either using a raw data stream from the edge, like a camera, or utilizing a pre-processed data stream, or recording the entire data stream in a backend database so that you can go and look for example, video feed from the last day or the last week or so on. Right. So the idea here is a camera pre-trained on objects using an MQTT stream, a limited access real-time stream, and remote management of farms. Right. So the idea is if you have a lot of farms out there, you can create a company that manages farms on the behalf of farmers, and they can do it using this kind of infrastructure. You can also have drones here, for example, that can capture data, for example. So these are some of the feeds that we get off the farm. They have particular vehicles on the farm. You have animal on the farm. You can look at, for example, the detection of animals on the farm. This is all YOLO feeds that are coming out of these Meraki cameras obtained from these farms. And this is something called Node-RED, which is a workflow system that allows us to build these kind of workflows, right? So we can have a Node-RED workflow, which can, for example, take a trigger. It can look at a path to the image. It can detect an image, identify an event using JSON, and push this event. And this event then is a message payload that goes to a subscriber that sits somewhere. So we basically implemented the backend workflows using Node-RED, utilizing Meraki cameras, but with these kind of edge devices, which are pre-processing this data. So that's another example of the edge, right? Where the edge really adds value by doing pre-processing of these video streams. And continuing on, so this was work done by Utterbury, which is a company that we worked with as part of the project. So what Utterbury did is they built a digital twin of the farm. So this is a digital twin. The farm has a number of gates. This is a tractor on the farm. So what happens is they put a geofence around the tractor. So that means if the tractor goes outside the geofence, it generates an alert, which can again be picked up. We have a gate, for example, the gate, which is a gate where the animals leave. So the gate also has a sensor. And when that sensor is triggered, that sensor alerts are sent out so the farmer knows when the gate is being opened and closed, or when the machinery on the farm goes beyond a geofence that has been set by the farmer. So this is another example of a farm here in Wales. We tried it on. So this is a kind of trigger you get. You get a trigger coming out. You say where the event is being generated from, and we can have an event log, right? A notification log, which can then be analyzed in the same way, but all coming from edge devices with edge servers which sit on the farm, which aggregate these events and periodically push these out to devices from the user. Okay, so that's one example. I'll give you a couple more examples of applications, right? Just to concretize why we really need the edge, right? Why this edge AI stuff is so cool. So this is another example. This is called Chetty Products and Factories. This is a EPSRC project that was finished about 2 years ago. So the idea of this project was that when you create a product in a factory, right? What you do is you can take the product like a bike or some other product in a factory. When the product is put out into the real world, the people might use the product in a way very different from what the designer had in mind, right? So what we need is we need to understand if we have sensors on the product, once the product leaves the factory, we want to know the ethnography and the patterns of use of the product, but do it in a privacy preserving manner, right? Because if we know what the designer had in mind when they build the product and the way that people use the product, we can analyze these patterns so that the next generation of the product is better because it takes into account the actual usage of the product versus what the designer had in mind. Right? So the concept is something called chatty products. So when the product leaves the factory, the product talks back to the factory, back to the designer to tell the designer how the product is being used. So you can create new forms of design. So it's a data-driven design suggestions can be made once the product is put into the wild so that we can next use rapid product manufacture, right? To change the product, the next generation of the product. So we have this continual loop of manufacturing from the point where the designer thinks of the product to the way the product is put into use to the next sequence of products and a continual improvement loop. And we call these chatty factories, right? So this was the idea. Now, this is a classic example of where the edge can play a really important part, right? Because The product is now the edge, because the product sensors that can monitor the use of the product are telling the factory how the product next generation can be improved, right? So that's the idea. So taking a bike, for example, an electric bike of some kind, we have sensors on the bike which can monitor, for example, the way the bike is used and the way the bike is driven, can help us generate the next generation of products. So just to drill down a little bit more, what we do is we use, again, a machine learning model, something called a denoising autoencoder. And this is how the idea that came out of this was, so we have an edge device, which is like the product that goes out there. The product has a set of sensors. We use an autoencoder to collect the data from devices on the product. And we use a threshold. So if, for example, sometimes you have noise on the sensor. And so what we do is we monitor the use of the product. And when the accuracy is below a certain threshold, what we do is we either ignore it or we label it as an unknown activity on the product. And then we use unsupervised machine learning model to create a label of how the product is being used, right? So, and then these labels that are semantic labels are then set back to a cloud environment. And what we do is these labels that are being generated show that the actual product is used in a way which is different from what the designer had expected, right? So this essentially causes a social chatter between devices in the use and the labels that are being generated from the use of the device. And again, federated learning can be used as a way to look at multiple products which are of the same model or the same category as a way to identify labels for these products. So here's an example. So if you have an accelerometer, for example, that sits on a device which captures the X, Y, Z coordinates of use of the product, when the use of the accelerator gives me an anomaly, that means that the product was being used in a way different from what the designer was expecting. That anomaly could be due to noise, or it might just be an anomaly that indicates that the product is being used differently to what I had expected. So what we do is we take the anomalies, and it's the anomalies that we encode with special labels that can be sent to the cloud, right? And these new labels can then be sent to the factory to reconsider and process at the cloud of how that product is being used. So there's a paper here that explains this in a little bit more detail. It uses a particular type of products with the human activity recognition data set to demonstrate how this kind of chatty products can be used in practice, utilizing this kind of edge computing model. So that's another example of where the edge can work. I'll just continue. So please ask questions, and I'll stop or increase in speed. So this is another example of using what we call a function-oriented edge. So if I have a data feed coming from a camera, what happens is this is the typical data processing pipeline, right? So I take a feed from a camera. So the first thing I do is I decode and extract a frame. I can resize that frame in some way. Then I look for an object within the frame, and then I try to extract the object, save it into a data store so I can associate a label with the object that I'm interested in. Right. So what we do in this particular project is we utilize function-oriented approaches, or you can have a number of what we call function-oriented systems that can sit on these devices. So these devices, which you can see here, F1 and F2, for example, might be on the edge, but the object analysis that happens can be on the cloud because it requires more computational power. Some of this pipeline, the object analysis pipeline, can run on edge devices. The rest can run on a data center. So here we use something called OpenWhisk, Apache OpenWhisk, which is a function-oriented platform that can do this kind of processing. And what we want to know essentially in this project is what is the overhead of running this processing on edge devices in terms of performance overhead of running these on edge devices, running it on devices which have more computational capacity and availability, right? So what we do is we run a number of performance analysis using the OpenWhisk with running on backend Docker containers, right? So this is the OpenWhisk architecture. The OpenWhisk has a node platform with a controller which can run different Kafka data streams, and we have different Docker containers which can run these functions. These functions can be invoked from this controller, but these functions can be physically running on different backend edge devices, right? So this is the idea. So we have a data stream, we have these edge layer, which can run on Raspberry Pi or other type of edge devices. And then we have a cloud layer. Cloud layer also runs OpenWhisk, but here we run a version of OpenWhisk called OpenWhisk Lite. This is a lower version of OpenWhisk, which you can deploy on these edge devices. So here you can see our deployment configuration, right? So the edge runs a Raspberry Pi GNU Linux. Cloud runs a Ubuntu version of this. We have other kinds of configuration management systems like Ensemble and Helm. If you looked at Ensemble, it's a configuration management system. We have different versions of Python and OpenCV, which is a image processing library. And we run TensorFlow, which is the machine learning model. On the edge device, we usually run a light version of TensorFlow. On cloud, we run a full version of TensorFlow. And these are the type of devices we have. Right? So on the cloud, we run a x86, Intel Xeon. On the edge, we have a Cortex A72, an ARM architecture. And these are running a lower version of OpenWhisk Lite. A cloud is running a full version. So that's a typical kind of software infrastructure for this continuum, right? So we have the sensors, the cameras, a light version, and a full version communicating across these three layers. So you can see this is the full version. The full version is able to give much more accuracy, right? So it's able to process a number of objects in this image, whereas the light version has lower accuracy. But that lower accuracy may be good enough, right, for most applications. The question is, how do we couple the two together so we have both the edge running a lower light version with the cloud running a more complex version together? So here we get some performance results, right? So function one, if I go back, just remind you, function one is running something simple. It's decoding the frame. Function two is then resizing the frame and so on. So as we move through the pipeline, the computational requirement increases, right? So here we can see the overheads of running these functions. So cold start means that we run the function from start. We launch the function. Warm start means that the function is already running, is constantly running, and we just use this function for processing this video stream. So here we look at the overheads of starting the functions, right? So cold and warm start time. So if the function is running on devices which have lower capacity, the overhead is very high, right? And so the other thing is here, the initialization time is high because initialization time on the Raspberry Pi, the computational power on the Pi is limited, so it requires a large computational overhead to initialize and run these functions. So this is a typical decision, right, that you would make when you're running edge and cloud together, is what is the overhead of restarting the function on your edge device versus a cloud environment? Because if the overhead is equivalent, you don't need the cloud, right? You can just run most of the processing on your edge device and ignore the cloud if the computational performance is equivalent. But in this case, it's not, right? So here it would make more sense to use a more powerful architecture compared to this. So this paper explains this performance overheads in a little bit more detail. So we then did other experiments. Here we have lower definition, standard definition, high definition, and very ultra high definition video. So we have frame of different sizes, right? These are frames with different number of the memory consumption and the average execution time of processing these frames. So you can see function F1, right, is running on the Pi. So really the execution time suddenly goes up, right? It goes from, approximately less than 100 milliseconds to about 527 milliseconds. Function F3, right, is the most computationally intensive. Because it's computationally intensive, frame sizes doesn't really influence much, because essentially, regardless of the complexity of the frame size, because the overhead is so high, your overall computational time is almost equivalent. Whereas with these two functions, the size of the frame really matters. And then this is the memory requirements, right, of function f1, f2, f3, and f4 with different size frames and different memory settings. So these are the kind of configurations, right, you would do as a systems designer when you're integrating edge and cloud together on machine learning workloads, in this case, frame processing with TensorFlow. Okay, so continuing on this, so everything I've told you so far has been on these type of pipelines, right? So I have the edge devices and cloud data center. What I didn't tell you, what happens about that thing in the middle, which we call the network, right? So what we are looking at also in Cardiff is how do we try to do federated learning and these kind of processing pipelines, but taking account of the intermediary network. So if you have a data network, how do I utilize the network also in addition to the edge and the data center? So for example, if you have federated learning, in federated learning, what happens is the edge device builds a machine learning model. So I have requests coming in from users, and I have a single aggregator which takes a number of machine learning models and combines these together. So what we're looking at here in this work is what we call hierarchical federation. So that means you don't have a single machine that aggregates these models, but you have multiple layers of aggregators. And some of these aggregators can actually sit inside the network, right? So you have a function that runs on a switch or some other kind of network component, but that network component is also acting as an aggregator. So we call this hierarchical federated learning. So the question we ask, right, is can building machine learning model that takes federation, can they take into account the architecture of the mobile edge computing environment? So here the idea is that in these federated learning models, the user devices can themselves become the aggregator in a federated learning framework. The question is, right, how do we place the aggregator? So how do we dynamically determine where the aggregator in a federated learning component should sit? Which device or which part of the network it should sit in? So where do we place the aggregator in a federated learning model? And how do we take network properties into account? So if you know, for example, that there's a particular network element, a switch or other network element, which has a very high connectivity compared to another network element, can we use the co-processing power, what we call network co-processors, and connectivity around that network co-processor to physically locate or place one of these federated learning components, right? So this whole work is looking at network properties as a way to utilize better machine learning placement by taking the network properties into account. So we have two papers on this. You can read these in more detail, which essentially looks at this model. And just to show you this, so this is the idea. So we have our user devices, right, that sit on one end. These devices can be a user mobile phone or a VR, for example, or XR equipment that sits at the edge. These devices can use a backend wireless or radio network to communicate with a base station. The base station can then communicate with edge data centers, what we call cloudlets. These cloudlets can then talk to an aggregator that can do the global aggregation of the model. And this global aggregation can then communicate with a backend cloud data center, right? So this is the idea. So the question is really that often when we look at edge and cloud, we only look at 1 and 6. But what about the network in the middle? Because the network itself is becoming more and more interesting and more intelligent over time. So this work is really understanding how the network architecture can be integrated into this machine learning processing by doing partial processing on the base stations and these intermediary cloudlets. So now the idea is that you have data center companies like Microsoft Azure, and Amazon Web Services with user devices, and you have network companies all working together to implement edge computing, right? So see, And that's really where some of this work is going. So we have this additional work that you can read about it in here. And the final thing I'll look at is integrating edge with a factory. So how does edge integrate with things like SCADA and PLCs, what we call the embedded edge? So in embedded edge, right, the idea is that you have a factory environment with sensors and edge nodes which can monitor essentially what happens in a production line or a factory environment. So the edge nodes can sit, these data centers can sit within a factory itself, right? So there's a paper here that looks at cybersecurity. But just to give you a picture, an image of this, so think of it like this, right? I have a production line that sits over here, and I have robots, industrial robots, which have actuators that sit on the industrial robots. I can have controllers, industrial controllers that can sit here. These are field side controllers that communicate with these actuators, which are industrial robots that sit at the edge. This data is channeled into a gateway node, and a PLC, a programmable logic controller like Siemens or Emerson, whatever your favorite PLCs are. These PLCs act as controllers that can talk to these actuators. And they typically use protocols like Modbus TCP or DNP3 or controller area network, CAN bus, and so on. So these are the type of data protocols you have within this environment. What happens is that this data is channeled through a human machine interface into a cloud data center across multiple layers of security. So what we want to do is take this stuff that happened in the cloud and push it directly into a factory, right? So the increasing use of edge devices, these aggregators that I mentioned can now sit inside the factory, right? So that opens up the potential for edge, what we call edge-enabled factories, which can then communicate with our back-end cloud infrastructure. The cloud doesn't disappear, right? We're not losing the cloud, but we're just giving more capacity capability to the edge. And so we can have these kinds of models. We can have field bus architectures like Modbus. We can have industrial Ethernet, and we can have wireless infrastructure. Now, all of these kinds of protocols are communicating within the factory to edge devices with different ranges in terms of communication range and different type of network topologies, right? This is what we call the embedded edge, but integrated within a factory environment. Okay, so I'll finish off in the last 5 minutes or so, if I may, with where is this going, right? Because how does industry get involved in this? And what would be, and I'll just, this is still preliminary work, and I'll open it up to questions after this, is this idea that think of everything I've said, right, according to this architecture. So we have a user who owns a user device. We have the data centers that sit at the edge. And then we have the micro data centers. These micro data centers are on-premise edge clouds. You can think of it as on-premise edge devices. And we can have different layers of these, which is what we call the hierarchical edge. You can have a data center that sits next to you inside a factory, but we can also have a data center that could be operated by a network provider, for example, right? So the question is, what are the business models, the revenue streams that we can have in a picture like this, right? Why would people want to deploy edge nodes? What's in it for them, right? And I speculate in this last part of this talk I'll just skip this part. Just give me 1 second. On business models and revenue streams for that architecture that I just described. Okay, so the first revenue stream is we can have these edge, what we call cloud data centers on one side, and we have the users. So what we need is orchestration or these components that can decide whether I should do my processing here or whether I should push my processing to a cloud data center. And so the idea is that every user device has an orchestration agent that decides, depending on an economic model, where to do the processing and to what level of accuracy. Should it be done on a micro data center? Should it be done on a cloud data center? And how does this connectivity between them influence that decision? So the first business model is what we call similar to what happens in a Wi-Fi access point, right? So we have a number of businesses today. You walk into a coffee shop will run a Wi-Fi access point, and they can charge you on a per hour basis or per month basis or whatever. So we have four different business models. One is called a dynamic uh, mobile edge, what we call a micro data center discovery. So what you do is that people can run these data centers, and you can pay to be part of these data centers. So Starbucks, for example, can run a data center. A coffee shop can run these data centers. And so the idea is that each of these represents different type of revenue streams for supporting these edge devices. We can have dynamic MDC discovery, pre-agreed MDC contracts, federation of these micro data centers, and micro data centers cloud data center operation. So what this means is, let me go through each of these quickly. In the dynamic MDC discovery, the idea is it's equivalent to finding a micro data center in the user vicinity. So in a vehicle, for example, is moving through the city, the vehicle owner or the manufacturer of the vehicle can subscribe to a micro data center to ship the data from the vehicle, right? So depends on the availability of micro data centers, security credentials, and types. So what happens is that the vehicle manufacturer or the user and the micro data center can form a partnership whereby you can say that if you ship this amount of data per month, this is the amount of revenue that you need to generate from that micro data center. Of course, there's no guarantee that the micro data center will achieve the quality of service target. But what you can do is that vehicles can have a preferred micro data center that is operated by one vendor. And the cloud providers can have alliances with micro data center providers, which is a revenue, what we call a revenue sharing model, where particular micro data center and cloud data centers can work together to utilize these edge data centers in some way. The second is where we have pre-agreed micro data center contracts. So here the contracts are, the idea is that of all the micro data centers, I form pre-agreed contracts with a small number of providers. And what happens is that when a user connects to these micro data centers, they have a preferential choice of data centers. So they say, it's very much like, when you take your mobile phone, you go to a different country, if you're coming from, say, 3 networks or Virgin Mobile or whatever your provider is, your provider will have pre-agreed contracts with other providers in other countries. So we can do the same for edge providers. So edge providers will form these preferential contracts, right, with particular micro data center providers, provided that these data center providers have pre-agreed service level agreements. So if you conform to your SLA targets, right, you are sharing a revenue stream with these micro data center providers. The third part is where we federate between different micro data center providers. So we have provider A and provider B, but these provider A and B form a federation where they share revenue models, provided that they conform to these pre-agreed federation that they form between each other. So it's equivalent to forming alliances between airline companies, whereby these micro data centers can come together to form alliances at the edge and share revenue depending on the number of users that you service within your area or your proximity. And finally, we have the idea that cloud data centers in the future, like Microsoft or Amazon, might decide to run their own edge devices, right? So what you do is you have a micro data centers, but the micro data center comes to you from a cloud provider. So the cloud provider moves into the edge space and runs their own micro data center in proximity to users. This is not such a big thing, because if you look at content distribution networks, CDNs operate like this, right? We have CDN servers which are in proximity to users, but they also run large data centers. And so CDNs working together with data centers can do exactly this. But this is CDN equivalent, but not just for content distribution, but also for running computational tasks. Right. So I'll finish off on that note. So I think the edge computing space offers tremendous opportunities, right? So this node that we're part of, the Edge AI Hub, is just can has so many opportunities. So existing data-driven applications making use of combination of cloud and edge systems, mechanisms for determining what should run where, right? What should run in the cloud, what should run on the edge, and how can we leverage on increasing complexity of our networks, increasing availability of applications inside the network. But how do we make money, right? What would be the revenue streams? What would be the incentives for companies to come and deploy these edge data centers working alongside cloud computing providers? So I really feel that in the future, we have this vision of what we call resource-aware machine learning. So the machine learning model should adapt to the resource on which it's run. So if I have a Raspberry Pi running on the edge, the machine learning model should run differently versus if I have an edge accelerator, which runs a quantum accelerator or a GPU or other device. So how does my machine learning model adapt depending on availability of devices on the edge? Thank you very much, and I'll stop there.
Omar, hopefully I've got a much better
Thanks, Paul.
signal now, and we can actually have a conversation. Apologies on the issues that we had there earlier. A fantastic call, very eloquently put out there, and I sincerely appreciate it. I have had to move to an echoey room just to get a bit of a better signal. So it's interesting to talk this leading edge technology, and I'm still trying to get Wi-Fi working in the house. But I'm really interested on the commercial model side of things that you talked about there, because I think it's something that we don't touch on very often in these sessions that we have. We very much have traditionally focused more on the technology landscape side of things and the new wave and so on. So this quite excites me because this is where I sit in the world, is actually more on the commercial side. Can you help me understand from what perspective you are looking at the commercial benefits to? Is it from a end customer value, or is it to an enterprise supplier model on what you constructed there?
Yeah, so certainly. So I think that the question here is that, if you have edge devices that are in proximity to users, utilizing existing network technologies, who should manage these cloud servers on our behalf? So there's increasing kind of, assumption that these edge devices are somehow also owned by the user, because they're operated by users, they're managed by users. But when I look at the farming case, and when we went out, farmers would not know how to run edge infrastructure. They will benefit from edge infrastructure, but they would not know how to run edge infrastructure. So what we were thinking is, you have these intermediary companies who come in and deploy this edge infrastructure, and then charge you on a per month or a per year basis. Mm-hmm. So I think there's this so edge computing offers a whole variety of new business models. Because of the question with cloud computing today is that cloud computing is often dominated by a few very major vendors. We cannot compete with these tier 3, tier 2 cloud providers, which have very large amounts of capital to invest. But we can have companies that could come in and offer edge infrastructure, but utilizing existing network technologies. And that opens up the space for potential revenue models.
Yeah. I mean, it's interesting, sort of like, I think what I hear you saying, which resonates with me an awful lot, is that there's a lot of focus and use cases and stories from the top end, which is funded from large enterprises funding other large enterprises to drive the adoption and get into autonomy and through automation and so on and so forth. And that there are so many use cases at that mid-market side of things where there is so much opportunity. From a personal perspective, one of my frustrations over the past couple of years is that there is a lot of technology coming through, and great companies like IoTech and Belina and bringing that capability of leveraging and utilizing edge. But when it comes down to the services, the integration of it, the actual people coming in, putting an edge unit there, setting up a camera, the resource is super hard to find to have people actually implementing this technology. That, to be fair, it has been the death of a number of projects I've worked on over the past few years, because you have some people that can come in and set up a CCTV camera infrastructure, so they know how to set up a camera, but that resource of being able to then connect it to the compute unit has been a bit of a cumbersome experience. And so within education, as you are, do you see that this is actually an opportunity of that education side of things of being less, I'd say, cloud focused in regards to development and engineering that we've had, based on the boom of cloud, that actually we're getting back to almost an opportunity here of having people on the street to be able to integrate and implement the technology?
Yeah, I think that's a very good point, Paul. I totally agree. I think that two answers to your, or two potential kind of discussion points is, I feel that there is an opportunity for edge verticals. So you have a farming vertical where you look at devices that are farm specific, and for companies to come in who specialize in edge infrastructure for farms. So what
Yeah.
they would do is they would choose a certain type of vendors to get these sensing technologies. You could have tethered drones, you could have particular soil sensing and so on. So what they do is they negotiate a contract with BT, for example, and say that I'm going to deploy this stuff. I'll purchase a network backend for you, and I'll give you a managed solution for your farm. And so you can do the same in factories, for example. So edge opens up the opportunity to have these specialist companies, which could be run by consultants who might have, worked for telco vendors, to come in and provide these kind of edge verticals. In terms of education, you're absolutely right, because I think the question is, the novelty is really what happens, because when you deploy your edge devices, you have much more control over them. I can go set up a lab here in Cardiff University, and I can actually buy edge devices. I
Yeah.
cannot compete with cloud vendors. First of all, cloud vendors will not let me touch their schedulers because it's their bread and butter. They will set up like a small VM instances for me to try out, but their real interesting power management, their infrastructure management stuff, they will never expose to other people.
Yeah, I mean, like the
So,
GPU access, right? I mean,
yeah,
which is
exactly.
their bread and butter at the moment. They're
Absolutely.
absolutely rinsing it for opportunity at the moment.
Yep. But I can set up an edge device next door.
Yeah,
I can buy an FPGA board. I can install HLS for ML, and I can use neural network models, and I can deploy it on FPGAs. And I
yeah,
can tell my students to do that. But to get the kind of real benefit of cloud infrastructures is very difficult.
yeah.
That's
And
my views anyway. Yeah.
yeah, I mean, one of the things that's jumping out to me is if you look at, and a number of people who watch these shows and stuff would have heard this pitch a number of times from me, but when I look at the boom of technology, like the PC did not truly boom until it started to get democratized and it was easier to use with the adoption of Windows as an example, and bringing that in, so it was more of an easier experience. If you think about the boom with the internet, was when it was democratized with the likes of WordPress. If you look at the boom of smartphones, there were smartphones for a number of years before the iPhone. The iPhone was the catalyst because it gave the ecosystem to do the full wrap of not just a nice device, but the marketplace, design principles on the experience, and so on and so forth. That made it easier for regular Joe to adopt, as well as techie early adopters. And if you look at how IoT's been bubbling, I mean, I did my first IoT project back in 2008 when I lived in Australia with the Department of Defense. And when you consider the length of time this has been going on, we seem to be in this loop of IoT and its effects, edge, and the adoption of AI, especially in computer vision and stuff. Is I truly believe the catalyst for the opportunity will happen when it's democratized. And so I was sort of like heading into a leading question earlier, is the opportunity here of black box solutions. So as you were saying, for a farm solution, if you had some configurable drones that literally go out like your robot does for your vacuum that we've got in the corner over there, it scans the room before it starts to work, so it knows the map of the room, or you can do it with the app and so on and so forth. That if you think about that experience for a farm to be able to then adopt things like drones and putting sensors on gates and stuff, that it's easy for the farmer and his work hands to do, rather than having to depend on a services consultant and having it productized that way. Maybe that's the opportunity of true scale. That edge is just the technology that's hidden behind it that makes the opportunity to work. You therefore then can choose if you retain that data and keep it private, or you enable it and connect it to cloud providers or to your supplier, you may be using a cloud provider, to then be able to enable that access to data. And I think I'm going to go on a rant here. The other thing that I'm finding really interesting, that's just really triggered in my mind there, is that data is now more evident gold than ever before, and which has really been brought to the forefront with Elon Musk's move at the weekend when he sold X to one of his other companies. Why? For the data off Twitter. And he's now just shown his cards on why he bought Twitter, and he's reduced the resources, reduced the costs to enable it to be sold at an operational efficiency. He wasn't bothered about it. He's not really bothered about the platform per se. It was the data from it. The next platform is what's the big thing, right? So then if you think about the opportunity of the data that's being computed at the edge and the opportunity that can come from this, maybe there's an opportunity of being able to trade your data for a commercial benefit as well.
Oh, absolutely. I couldn't agree more. I mean, if you have, just as you're saying, Paul, if you have these verticals, then there might be data science opportunities to build dashboards, to build other kinds of analysis on the data, which you could then feed back into the farms or other factories. I think sometimes also the issue is that the data. So this is the other thing. So the data that the farmers collect sometimes is very sensitive data, because, for example, in certain countries, when you have emissions from farms, you're liable to say a certain penalty if you violate those legal emission targets. So sometimes the data farmers don't want to share the data, because the question is that so the data has to remain on the farm, and they have complete sovereignty on that data, which is where the edge really benefits, because the data is not leaving. So if you have a farm side unit or sits on the farm, the farmers or a cloud that an edge device is sitting in the factory, the owners of those environments have complete authority on the data. And then, so although you want to monetize some of it, but you decide what you want to monetize. And I think that also gives you this kind of data sovereignty, which an edge provides, which a cloud doesn't. I have no idea what happens to my data when it goes to a data center, because unless it's encrypted or unless I use homomorphic encryption or something like that, there's no guarantees on what happens. But the edge gives you that ability of having edge privacy, which others devices don't.
Yeah, I think it's really interesting. Like if you think about how Apple's moved with the iPhone, and they're trying to push that there, private, trying to help you make your data as private as possible, but give you the option if you want to open it up to third parties for that access. And I think it's kind of, similar to what you're saying there, is that one of the big tick in the box, and like my past 8 years, 10 years in working in Edge, I think it's 8 years now, the majority of the use cases and value that customers saw with the adoption of the technology, they had a problem statement. We went and talked about the technology that could help it. But one of the key things was on-prem, not having the data in the cloud. And if you think about medical, if you think about, interestingly, the biggest ones being manufacturing, who do not want their data out of their factory. And then having those micro data centers connected, so you've got the near edge, the edge, the near edge, and then the network edge layers of that onion on where the data goes, depending on where it needs to, actually adds an awful lot of value, as well as helping reduce costs, because you can have multiple lower cost devices that may not depend on a GPU. You may be able to be inferenced with a CPU or an iGPU or an NPU, which are dramatically lower cost than currently GPU costs. Plus, one of the other things, which may be a bullet point might want to add onto your deck, is one of the key things about Edge is power management. If you think about on a farm, you're potentially going to be depending on solar on some of the devices at the edge. So the lower compute and silicon decision then goes on the power management requirements that you have there. If it's in the factory, again, they're very conscious of not trying to keep their energy uses as efficient as possible, because the way that they, especially in the UK and Europe, the way they purchase energy, they have to forecast it. If they go over that forecast, they get penalized. If they under forecast, they get penalized. So they've got to be super smart with it as well.
We agree with that. So I think you raised a very important question, Paul. So with battery technologies, I think the use of edge energy is going to become more interesting.
Oh yeah.
And I think so there are even people talking about hydrogen and other types of fuel cells that can sit at the edge of the network, which could help power some of these devices. And you will have full control over how that energy management is undertaking.
Yeah,
But
it's
you're
that
absolutely-
win-win with it, right? It's
yeah,
the
absolutely.
energy that's helping supply the edge, but also the edge that's helping manage the power supply kind of loop with
Absolutely.
it as well.
Absolutely.
We've got a one question statement here. So given the cellular IoT today is underpinned by roaming SIMs, how do the business models incentivize the visited telco supporting edge compute routing for visited SIMs from competing telcos?
Yeah, so I think that's a good question. So I think what I was thinking is that we separate out the way the network is provisioned from the services that the edge is providing. So the network provisioning can happen through, as you mentioned, roaming SIMs, but it's a layering of services on top of that would be done through these edge data centers, or what we call micro data centers. So, you might decide to choose network from whatever telco vendor you want, but the service that you run on it might be supported through different edge, could be through this federation model. So so I think we need to separate out the service from the network provisioning itself.
Yeah, I think it's an interesting amount. My background's telecom, and as much as they try to evolve and move away and be more innovative rather than just offering SIMs, they fall into that loop of their budgets of depending on the SIM card and connectivity side of things. And I was chatting to some ex-colleagues of mine that are now at the Vodafone IoT company that's partnered with Microsoft. And I was saying, hey, how is it? You've moved away from the shackles of the network, so to speak. And like, we still sell SIM cards. That's our big thing is SIM cards. Everything else is nice slideware. I'm sure I'll be corrected on that in the not too distant future.
I'm just
but that
trying
was a statement from an event this week.
No, that's fantastic. I'm going to put the link to the slides. These are available in Dropbox. I would welcome feedback from colleagues. You guys in Newcastle are actually leading the hub. So, I hope that you have a lot of new companies that come out in the region to actually benefit from the expertise that you have. So, yeah.
I certainly hope so. And I was at the Northeast Automotive Awards a couple of weeks ago, and it was amazing to be talking to so many managing directors of suppliers to Nissan and Komatsu who were saying, hey, I want to do automation, I want to do autonomy. Where do I start? They're struggling to find people, so I've actually been signposting to the hub to get that help to get started and at least be educated a little bit. But you've got the slides there. So we will be sharing the slides. We'll also share the link on the website as well. I'll get that from Omar and get that shared on the website. As I mentioned, we've got another great talk coming up next month, which is beer brewing at the edge with Sean Lawrence. Really great talk. Thanks to, as always, John Staveley for organising this. And I think John will possibly lead that conversation. I'm just wondering if we'll get any free beer sent as well to drink whilst we're having this talk. Sean, if you hear me, let me know. And on that, Omar, thank you very much.
Thank you, Paul.
And
Thanks.
Really appreciate it. Look forward to catching up very, very soon with the hub as well. Thanks for support.
Thank you. Take care.
Thanks,
Thank
everyone.
you. Bye.
Good night.